Hello, and thanks for checking out Chemistry Connections on the Hopewell Valley Student Podcasting Network, a proud partner of hvspn.com, where students come together to publish content to share with the world. The opinions represented within this episode are those of the content creators only. Please enjoy the show.
I'm Alana.
And I'm Neve.
And welcome to this week's episode of Chemistry Connections, where today we will be discussing the chemistry of everyone's favorite chemical, caffeine. Caffeine is a chemical compound which is commonly found in beverages, and it serves as a central nervous system stimulant, and it's the most widely used CNS stimulant in the world.
Whether it be in your morning coffee, your pre-workout energy drink, or any other type of beverage, people these days can't get enough of this energizing substance.
In 1 year, Americans will consume over 971 tons of pure caffeine. That's a lot of caffeine.
Since we ourselves consume so much of it, it's probably important to understand it better.
Caffeine, at its foundation, is just a combination of carbon, hydrogen, nitrogen, and oxygen atoms with a chemical structure of C8H10N4O2.
The molecule has 25 sigma bonds and 4 pi bonds. Sigma bonds are directly in line with the nuclei of the bonding atoms. Pi bonds, on the other hand, are when there are multiple bonding spots located either above or below the nuclei of the bonding atoms.
Each single bond is made up of 1 sigma bond, and each double bond is made up of 1 sigma and 1 pi bond. And because of this, there are 25 sigma bonds and 4 pi bonds that make up a caffeine molecule.
All the bonds in caffeine molecules are stable covalent bonds, as the bonding allows each of the atoms to completely fill its outer valence shell.
These bonds are slightly polar, making the caffeine molecule a polar molecule. The molecule is polar because there are electronegativity differences between the oxygen and carbon atoms as well as the nitrogen and carbon atoms, which allows these oxygen and nitrogen atoms to slightly pull the electrons towards them in the bond.
Because the caffeine molecule is more polar, there are dipole moments formed between atoms. There are dipole-dipole IMFs that exist between atoms in this molecule. Additionally, the caffeine molecule has London dispersion forces, which are also known as LDFs. LDFs exist between all particles, regardless of their polarity.
The covalent bonds in a caffeine molecule are very strong, and the strength of these bonds lend themselves to a high melting point at around 230 degrees.
The stronger the bond, the stronger the IMFs between the molecules, meaning there's more energy needed to break these bonds. In this case, energy comes in the form of heat, meaning that caffeine has a very high melting point.
The covalent bonds in the caffeine molecule also allow for hydrogen bonding to occur between caffeine and water molecules. The strongest hydrogen bonds form at the top CO group, but additional hydrogen bonds can form between water and the bottom CO group, as well as between the nitrogen atoms and water molecules.
It's also important to understand that even though most people may think caffeine is super acidic, it's only a weak acid, meaning it can be protonated by a strong base.
This means that caffeine wants to give hydrogen atoms to basic substances.
One reason that caffeine is acidic has to do with the structure of its outer nitrogen atoms. Nitrogen atoms have a lone pair of electrons in their outer shell, which are readily available to give protons, also known as hydrogen atoms.
Because of this, caffeine can react with other substances which are bases in order to form salts.
It's not typical in nature for the formation of salts to happen, as the only times that caffeine typically forms salts are in lab settings.
Caffeine hydrochloride, caffeine sodium benzoate, and caffeine sulfate are just a few types of the many caffeine salts that can be formed.
In your morning cup of coffee, however, your caffeine is likely in the form of a free alkaloid. This means that the caffeine molecules are not bonded to any other type of molecules.
And this is because caffeine is a very, very weak acid.
The molecule is such a weak acid that it's practically neutral. In fact, the pH is only slightly above 7, which, since it's so close to the neutral on the pH scale, really doesn't mean much.
The addition of sugar or cream to your coffee can have impacts on the pH, though the effects are very minimal, as the pHs of milk and sugar are both very close to being neutral.
The acid may be weak, but I definitely like my coffee strong.
So we had many topics to choose from, and we decided to land on caffeine.
We are particularly interested in the topic of caffeine since we ourselves are such fanatics for it.
We've gotten very good at making it and ordering it. What's your go-to coffee, Neve?
If I'm making it at home, I usually like a cold brew with some almond milk and sugar, or maybe that caramel flavor sauce that you can get from the store. If I'm ordering it, depends if it's Dunkin' or Starbucks. My Dunkin' order is probably a medium caramel iced coffee, and my Starbucks order is probably a brown sugar oat milk shake and espresso.
Ooh, those are really good choices. I could definitely go for some of those right now. If I'm making it myself, it's either going to be like a lavender latte or a caramel latte because those are definitely my two favorite flavors. If it's Dunkin', though, it's got to be an iced coffee with oat milk and caramel. But then from Starbucks, I also, like you, either get a shaken espresso or I'll get a latte with some sort of oat milk and some sort of syrup.
I could really go for a coffee right now.
Ugh, me too. Oftentimes, though, I find myself over-consuming caffeine. So it's really important to understand the chemical properties and the effects that caffeine can have on your brain and your body.
Caffeine is a fascinating molecule, though, since it has so many attributes. There's many different chemicals that caffeine causes the human brain and body to produce.
Norepinephrine, which is a neurotransmitter and a hormone, plays a really important role in your body's fight or flight response.
Dopamine acts on areas of your brain to give you feelings of pleasure, satisfaction, and motivation. A lot of times, this is associated with happiness.
And serotonin, also sometimes associated with happiness, is a chemical that carries messages between nerve cells in the brain and throughout your body.
These are just a few of the many effects that caffeine has on the human brain. These qualities also contribute to the addictive trait of many of our favorite caffeinated beverages.
Did you know that caffeine is actually one of the most widely used drugs in the world?
Caffeine's a drug?
Yes, because of all the addictive properties of it, which are just the feelings of your brain creating all these happiness hormones. The body often finds itself chasing this need to drink caffeine in order to keep producing these chemicals.
That's so interesting, especially because the age of people that drink caffeine is definitely getting a lot lower. I saw a 5-year-old drinking a coffee at Starbucks last week.
I also saw a 5-year-old. My sister drinks caffeine all the time, too. It's really crazy.
It's an epidemic.
It really is. Thank you guys so much for listening to this episode of Chemistry Connections. For more student-ran podcasts and digital content, please make sure to visit www.hvspn.com. Thank you.